We have been overwhelmed by your response. Many people have posed the Optica question direct to my team and I. They know what we do for them. But what can active leaders in optics and photonics do for us? The answer is simple. By joining Optica as a corporate member, you encourage us to expand our trusted global network and support our new range of services. Get deep insights into what's next for your sector in photonics with free access to over 90 market reports, plus exclusive access to the PowerPoint slides for the in-person meetings. And corporate members get exclusive access to all Optica industry meetings in 2024, including...
If you are an investor in photonics, you'll recognize where I am now. Hello from Frankfurt Messe, which will be the venue for the ECO Conference 2024.
The third Tech Summit in Silicon Valley. The Optica Laser Congress in Osaka, Japan. Plus the Optica Quantum Industry Summit, this time in Bristol, UK. And remember, being a corporate member of Optica also gives you discounted access to many partner events, such as Peak Summit Europe, Driving Vision News, and Peak International. Hello everyone and welcome. Welcome to the Optica online industry meeting on quantum sensing. I must say I'm overwhelmed once again by the whole support from the industry. We have over 400 people registered for the meeting today. Together between the Zoom room here and the YouTube channel, we expect to have a very interactive next 90 minutes to address the need of certain companies who are here to showcase what they do, but most important, what other industry can do for them to help them realize their business. As I said, my name is Jose Pozo. I'm the Chief Technology Officer of Optica, and I'm speaking on behalf of 184 staff, 24,000 individual members, and almost 600 corporate members. Thank you for the ever-growing Optica corporate network of companies who are here to find meaningful connections. Today is all about quantum sensing, and this is not a webinar. If you are here to find potential partners, suppliers, and customers. So please, all of you, start thinking about your Optica question. What can you do for others in the meeting, and what can others do for you? This meeting wouldn't be possible with the support of our sponsor today, so thank you very much. OptiWave, or Optica corporate member, providing design software and simulation tools for optical design and photonic integrated circuit design. Thank you very much, OptiWave. Today is all about quantum sensing. I have prepared for you 4 showcases of companies who are here to try to find customers, suppliers, and partners. They're going to share with us what they do and how we can help them. First, Cerca Magnetics Limited. They are going to show the world's first commercial, fully integrated brain imaging device based on optically pumped magnetometers. Then Vector Atomic. Thank you very much for your support, Vector Atomic. System-level quantum sensing solutions for applications that go from GPS-free navigation all the way to telecoms and computing. Then, coming all the way from Texas, Inflection is going to talk to us about the quantum solutions for timing, sensing, and navigation. And last but definitely not least, the last one, really the one to stay, SV Quantum, is going to talk to us about engineering nitrogen vacancies to measure Earth waves. This is not a webinar. These companies are going to tell us what they do, but most important, they are going to tell us how we can help them. And together with them, we have a few sets of companies who are here offering solutions for those integrators to adopt. Leonardo DRS, Keysight, Freedom Photonics, Covation, or OE Waves have prepared one slide for us. But everyone in the meeting, everyone here today is welcome to show what they do to match the need of vector atomic, Cerca Magnetics, Inflection, and SV Quantum. As usually, I would like to remind everyone that Optica is many things, and Optica is also an industry network. If you want to support us, the only way to support us is to become Optica corporate members. So please join us in our network. All our members get access to our events, but also get access to our library or market report. So you are looking for the presentations after this meeting, or the presentations after any meeting, or latest market data from companies like Thematis, like Mordo, like Joule. We have free access for all our corporate members. For any other information about this, just drop me an email. It's very easy to join as a corporate member. I also would like to remind that this meeting is part of a series of events. Today we have quantum sensing, right down 25th of June. On that day, the online industry meeting will be on cancer diagnosis and treatment for prostate and breast. We're showcasing the technology of our corporate members, understanding what they do on that, and matching them with the need of medical doctors. It's a very important meeting, 25th of June. Please be there on our online industry meeting series. And also, last but not least, this meeting is showcased here in Zoom, but at the same time also in YouTube. So let me say hello to the YouTubers in the world. Hello, YouTubers. If you have any question, please write it in the chat and I will read it in the room. Also, after the meeting, let us know with which companies would you like to connect and we will make the introduction. And of course, this is also valid for the people here with me in the Zoom room. If you have any question, please write in the chat, raise your hand virtually or physically, or write in the Q&A. Please make sure you ask questions. We need your questions. Without your questions, this becomes a very, very boring meeting. And believe me, the next 90 minutes are going to be many things, but not boring. Let's start. And I would like to start by giving the floor to a company, which was my colleague, Dr. Pooja Diamat, who has been scouting companies, who's very excited about why Cerca Magnetics was going to open the meeting today. David Volger, thank you very much for taking the honor of kicking off the quantum sensing event. The floor and the attention of everyone. We are global today, coming from ITF, IMEC Technology for in Antwerp. The floor is yours.
Thank you very much, Jose. And I should start by saying you're one of the few people that actually says the name how it's meant to be said. So thank you for that. So I am going to tell you today a bit about Cerca Magnetics and how we have brought to market a brain imaging piece of equipment that is based on optically pumped magnetometers. So I'm just going to try and get these slides to move on. There you go. So we've been on a journey since 2016 to develop this technology. Initially, we were using a conventional form of magnetoencephalography, or MEG for short, SQUID-MEG, that uses superconducting quantum interference devices for seeing the magnetism in the brain. In 2016, a team at the University of Nottingham worked out that they could, via simulations, that if we could get sensors closer to the head, we would be able to get better spatial resolution and also better signal-to-noise ratios. At this point, it was very much a simulation, and actually sensors were starting to be developed, but they weren't fully available in a commercial way. At the same time, we realized when the sensors were available, for this to work, we would need a very, very low field environment. So we were also working on shielding design to enable us to see these sub-nanotesla fields from the body. In 2017, we got our first OPM optically pumped magnetometer sensor, which uses the quantum effects of the rubidium atom in the vapor cell in order to measure very low magnetic fields. We got our very first quantum optically pumped magnetometer, and you'll see in the picture there, this is our first scan using this sensor. What you can't see from that picture is actually the person being scanned had their head securely held to the bed at the time, was not able to move in any way, and actually in a fairly scary looking mask we were able to get data where we held them dead still. We continued to get further sensors, and also continued to develop the magnetic shielding to enable us to get to lower fields. So we were enabled to actually get some movement-based data, so where people were able to move the head in more naturalistic ways. We still had a very scary-looking head cast that held people still, and you can see in 2018, our CTO, as she is now, Dr. Elena Boto, actually got a 16 sensor recording, and at that point the data from this enabled us to be published in Nature, so quite a seminal moment for the research into this. We continued to develop, and in 2019 we were able to get our first pediatric measurements and carried on forward until right in the middle of the pandemic we decided that we had managed to get 50 channels, 50 sensor recording, and we'd actually been able to evaluate the data, and it was as good, if not better, than the conventional MEG systems. At this point, we decided that it made sense for us to form a company to really enable us to commercialize this technology. We formed the company on the 24th of July 2020. Most people were in their houses still hiding from the pandemic. We were the crazy ones thinking about actually forming a startup. But actually, since we formed, we've been profitable in every year of trading. We delivered 2 systems in our first year, so one to Sick Kids Hospital in Toronto in Canada and one to Young Epilepsy, a charity in the UK. And after this, we've continued to install systems. So we've got a number of systems in the US and a number of systems in Europe. It is worth noting at this point, our systems are not clinically approved in any market. So at the moment, they are delivered for research only, but we are starting to do some really good research, and certainly the unit in Sick Kids has been using our system to look at children with autism, and are getting some really good data in younger brothers and sisters of children with autism. So to tell you a bit more about the system, so SquidMeg gives you very good spatial and signal to noise, but it has some issues in that it is a one size fits all. You can also see that unit there. The challenge is it's very difficult, especially with young children, to get them to want to go into one of these units. So what the problem we're overcoming to a large degree is to make this life cycle compliant, so it's usable for young children. There's a lot of other benefits for our system, but I think they can be narrowed down to flexibility. We really can scan anyone from babies to adults, and that's important not just for the younger age group, so we've scanned down to 6 months old, but also for, say, people with dementia. Again, if you look on the left-hand side of this slide, that big unit for someone in their older stages of life, maybe with dementia or Parkinson's, it's very difficult to get them to sit still and have a scan. Our scanners are robust to motion, so you can actually move your head freely during the scan. Again, for any of you that have got children, keeping a 3-year-old still, even while watching, say, Bluey on television, is difficult enough. Keeping them still in a scanner is nigh on impossible. Our scanner enables that naturalistic movement and that we can still scan. We've got increased sensitivity and spatial resolution. And a big one for us is that the scanner is cheaper, both in terms of original unit cost, but ongoing costs. There is no reliance on helium cryogenics. So this really reduces the ongoing costs of the unit. So what is it that Cerca offer? Well, we actually offer a fully integrated OPM MEG system based on the optically pumped magnetometers. But when we leave site, we bring together all the bits of that system, all the disparate bits from the software, the hardware, even the projector to deliver the stimulus for the patient or the participant in the study, so that when we leave site, our sites that we've delivered to, providing they have the right ethical approval and things, are able to scan immediately and produce neuroimaging data. That's very important in that we are delivering a fully integrated neuroimaging system. So a bit more about the system, and you can actually see one of our sites here, which is probably the interesting thing on the right-hand side here. You'll see there's one side here. This is the server rack and the electronics required to run the system. And on the top photo there, you can actually see the system there. So within that room, again, it's a much more naturalistic environment without the big, heavy scanner, where children, parents can be in the room with the child, and we can project onto the walls, so it makes it a much more friendly, easy environment to be scanned in. Some of the cool things that we've continued to do, obviously, the free range of movement allows us to do things that haven't previously been possible in neuroimaging. One of these is being able to scan 2 people at once. Now, what I should say, this is a research system, so the cables are much better managed in our delivered systems. But what we were trying to do here is be able to scan 2 people so we can start to see the interactions between people. We thought, what can we do to do that? And one of the things we came up with was playing a game of ping pong. So you can actually see our CTO and our chairman playing ping pong here. And what we saw in the data, as one hits, their motor cortex is operating. As the other one is receiving, their visual cortex is operating. Exactly what we would expect to see, and they're correlated in the antiphrase. Now, what does that actually tell us? Not much in the grand scheme of things, but potentially if we could look at a baby and a parent as the baby's developing, we would get some data there. So this is really a cool experiment to prove that it is possible to scan 2 people at once. And it's something that has not previously been possible in this type of neuroimaging scanner. So it really was something where we were able to go to the next level. This is just showing that data, so you can see for any neuroscientists amongst you, you can see the motor cortex and the visual cortex as they light up. That is effectively a very quick whistle-stop tour of Cerca and what we are doing. I would be very happy to accept any questions, and we are also happy to hear from anyone who is online today at a later point and wants more detail.
All right, great presentation, sir, David. And this was seems to be changing the whole neuroimaging landscape quite a lot. Now, let me ask you the first question. And that's the Optica question, basically. What can you do for others and what others can do for you? What is it that you're looking for and what are the challenges?
It's a difficult one, really, because actually at the moment, our challenges are around medical regulation and getting the clinical approval. We do have a current supplier of the OPM sensors. I do know that they have some challenges with the lasers and things. So if there are laser manufacturers on the call, then I would be keen to speak to them. And I'm not in the detail of the actual sensor and how that's put together. I'm more on the system integration side. But I'm happy to accept if anyone emails and wants to discuss further, I can put them in touch with the right people who would be able to discuss further.
You ask about laser companies, and there are actually many of them in the meeting today, and some of them are speaking. Actually, let me for that matter, let me bring in Jason from DRS. Jason, David is looking for lasers. What is it that you guys can do for him?
Yeah, so I can either speak on it now or speak on it a little bit later, but we do have a new commercial product offering. We call it Stretto, but it's an external cavity diode laser that's been ruggedized, and we can essentially design this laser to hit any one of those atomic transitions between, the UV, I think 369 nanometers up to about 1800 nanometers. So rubidium, I know you mentioned rubidium has an atomic transition in there. And so we can kind of configure our laser source, a ruggedized stable laser source, to hit that atomic transition to give you very fine control over that atom.
So Jason, you actually have a one slide presentation, right? Why don't you put it up and let's go over that?
Yeah, certainly. If you give me just 1 second here. Yeah, so hopefully everybody can see my screen now. And so what we're showing here is exactly what I had just mentioned. Is the commercial product offering that we have called Stretto. Oh, excuse me. Let me share this one more time. Pardon me. But yeah, so we've got this commercial product offering called Stretto. We have put in a fair amount of effort to ruggedize this. We have existing capability and other type of technology in ruggedizing different types of laser sources. And, you think, why would this be important for laboratory or other types of settings? It makes it so that the laser is no longer part of the experiment. It's something that you can install and ensure that it will work over a long period of time. A cute little demonstration. So if I can get this video to play, we took this laser, we locked it onto a pound river hull, and essentially took a dead blow hammer and introduced 150 G of shock force onto the optical table that the laser was mounted on. And we can see it very quickly returns to its locking state. The laser itself is also very narrow, or it has a very narrow free running line width. When we lock this laser cavity, we've been able to show that the line width is less than a kilohertz. So a very good, very pure laser source of light. And we're really looking to enable all of these quantum applications going forward, whether this be quantum sensing, as we're talking about today, or integrating these into quantum computers or other types of applications there. One other thing that I want to mention here is that we've been able to successfully demonstrate an integration of a PIC into our external cavity diode laser. The first demonstration showed a great ability to control amplitude, we effectively demonstrated amplitude and phase modulation with the PIC that we've integrated into here. But the exciting part is that this is a pretty new technology. Photonic integrated circuits are not necessarily new, but photonic integrated circuits working in the visible spectrum is kind of an exciting development that we've been pushing forward. And so,
that's great. And actually, I mean, one question that we ask from anyone within the technology, within the photonics technology, is it pickable? Can it be pick be done with it? And you have addressed that. Now let me ask David, bring him back to the conversation. So Jason mentioned a very narrow line width. It's 1 kilohertz of narrow. Is that something that is good enough for you? What are you looking for? What are your requirements for the line width of the laser?
To be honest, I'm not 100% sure. I'm not involved in that element of the business. I'm more on the neuroimaging side, so I would need to speak to my scientists. So what I can do is take Jason's sort of information and go back to them, if that's okay. Sorry, Jason.
No, not a problem.
That's something that we actually at Optica can help. We will connect you after the call and make sure that you get connected and this conversation goes forward. All right, we have a question from Gianvito Lucivero, and it's how important is the geometry of the sensor array for mega applications? And is that go ahead?
Sorry, I read it as I said, so I'm jumping ahead
Okay.
before you'd read it, but can you give any benefit from further integration between vapor cells and integrated photonics? It's a great question. It's very important, the geometry of the sensor array. Crosstalk between sensors is one of the biggest challenges to overcome in the sensor array. To get, again, we're talking sub-nanotesla, picotesla level fields. To really be able to see those, you need to control that crosstalk to a very high level. So is it a topic with ongoing R&D? Yes, there's a lot of work that we're doing on the R&D of the sensor array and how we deal with that crosstalk, both in the sensors, but actually in the software as well. And could we get any benefit from further integration between vapor cells and integrated photonics? Yes. So the OPM sensor is integrated with the laser, the vapor cell, the coils for controlling the fields within the vapor cell are fairly integrated, but it's certainly something that is interesting and we need further R&D in. So yes, really good question.
Okay, and we have another question actually from Phoebe Hengden from Rex. Phoebe, why don't you put your camera on and let us know what you think, and what's the question for David?
Hi, sorry, I don't have a camera, but I was just wondering if you had, because you had the nice slide about these ECDL lasers from daylight on a PIC, and I was wondering if you had any numbers about power consumption for your various different PIC solutions.
So, we've got a VPI of less than 0.4 of a watt, or 0.4 of a volt, excuse me. Are you talking wall power, or what type of power consumption are you looking for?
Even just for the lasers.
Okay, yeah, fair. I can follow up with the exact power consumption figures if you'd like.
Yeah, that would be super interesting.
Absolutely.
Because we're looking at, like field kind of solutions, something that can actually be portable, outside the lab. So that's why I was wondering.
Phoebe,
Yeah,
many people
absolutely
here,
understood.
Phoebe, many people here don't know MiraX, and this is a very interesting company. Phoebe, could you tell us in one sentence what MiraX is?
Yeah, sure. So MiraX is a small startup in Switzerland, and we are working generally on quantum technologies. But our main product is about quantum RF to microwave to optical conversion. But we're also looking on this applications of this technology for quantum sensing as well as for quantum computing. So basically aiding quantum computers to connect them.
All right, and we have one more question from Siamak from Optica. Siamak, why don't you unmute yourself and let us know your question?
Sure. Thanks, Puya. I actually have a question for Sierra, for David. So thanks for the great presentation. I've been actually looking into MEG companies' devices, and it turns out that oftentimes the lasers are integrated into the sensors itself. So that also makes sense because it makes things probably more compact. And regarding the lasers that would be needed for this, I think I've seen people using like small swap lasers. The peak lasers that Optica has been working on, the first frequency or wavelength that we started is compatible with rubidium. So I think it would be a good choice for making it kind of integrated with the system to probably make things as small and as low weight as possible.
I would fully agree. There's two basic ways of doing it: either the integrated laser in the sensor head, or the fiber optics and the laser separate to the sensor head. So both sort of methods are viable and have been shown, demonstrated to work. So there's challenges and sort of benefits of either of the two systems, really. So yeah, I would be interested to put you in touch with our scientists, whichever of the two systems you think would be most appropriate based on your product line.
Sure. I'm happy to have a follow-up call with you guys on that.
Yeah.
Okay, and just as a reminder, anyone within this call that wants to get connected to others, feel free to reach out to me or the other tech directors, Jose, to Jose, our other tech directors, Olga and Helena are on the call and ready to help you all. Well, just as I was about to move on to the to the next call, another question came in, and I have to take this. So it's from Andreas Volker from CSEM. Andreas, why don't you unmute yourself and ask this question, and then after that we will move on to the next call.
Hi everyone. Thanks for this interesting presentation. I was especially intrigued by your sensor and the vapor cell that you have. At CSEM, we've been working for years on atomic clocks using rubidium cells, making them at wafer scale in large quantities. And now I was not aware, do you have that already integrated at large volume? Can you produce your sensors easily on wafer scale?
So they're not a wafer scale, they're about the size of a sugar cube, so they're a bit bigger than a wafer scale. And the vapor cell is probably 5 millimeters across, it's 5 millimeters tall. So again, I'm not an expert on that side of it, Andreas, unfortunately. So like I can take your details and we can chat with one of the scientists who is involved in the vapor cell and the actual sensor itself.
Yeah, I think we should follow up on that. Maybe we have some interesting solution there for you.
That would be really interesting. I mean, you ask what's the ideal vapor cell size? The smaller the better, because that will enable us to have more round the head. What we found we found the law of diminishing returns to some degree, though, with the heat. We have to control heat at the scalp surface. For medical devices, that can't exceed 40 degrees at centigrade at the surface of the head. So as you cluster the sensors closer, you get a bigger heat buildup, as you would imagine.
Yes, I'm aware. Okay, let's talk later about this.
That would be really good. Cheers.
Thank you very much, David. And there is a question coming on the YouTube chat, and I would like to welcome also the YouTube watchers here. Please write your questions there. The question is coming from John Pugh from University of Bristol. David, are there any issues with the sensor head heating up?
Oh, I think I probably answered that one to some degree. Yes, it is one of our biggest challenges for a medical device, that you have to work out how to restrict that heat to 40 degrees, and we want to scan people for up to an hour. So we need to have the ability to restrict the sensor heat to 40 degrees centigrade and be able to scan for an hour. We've also, the sensors are very sensitive to any form of airflow. So an air-cooled type system, we can actually start to see that in the sensors. So there are challenges, but again, that's an engineering challenge as we're developing the system.
Thank you very much, David. Puya, why don't we meet the Vector Atomics people?
Oh, sure. Yeah, and actually, I'm very excited about this next talk from Vector Atomics. Let's bring in Jamil Abu Shair from Vector Atomic. The floor and attention of everyone, the floor is yours, Jamil. All yours.
I think we may be having some connectivity problems with Jamil.
I'm here. I'm okay. Sorry, I thought there was one talking between me. Just give me 1 second.
Okay. And Jamil, if you don't mind putting your camera on. We'd like to,
Sure.
you have a smiley face on the photo. We'd like to see it in the real.
Yeah, I will. Let's see.
I did like that in the previous presentation, we asked who are the laser manufacturers. Let's see which community we're addressing today. Jamil, as Puya said, the floor is yours.
So you guys are able to see this and see the slides, I hope?
Crystal clear.
Okay,
Yep.
great. All right, thanks everyone. Sorry for the confusion. Good morning. It's a little early for me. I'm Jamil Shair. I'm CEO and co-founder of Vector Atomic. We're building atomic clocks and inertial sensors for applications including navigation, communications, and geophysical exploration. So given the short time I have today, I'm going to mostly focus on our clock work, and through GPS, atomic timekeeping already rules our daily lives. So from navigating nuclear submarines to navigating dating profiles, GPS is pretty much baked into everything we do. It's already generated more than $1 trillion in economic impact in the US alone. And when it's not available, like we currently see in the Ukraine, it poses real challenges. So GPS is built on 1960s atomic clock technology. It provides global timing in 10 nanosecond intervals, 10 billionths of a second. Our goal is to globally distribute time at 10 picoseconds, so 10 trillionths of a second. And in that process, hopefully unlock that next $1 trillion of economic impact. So roughly speaking, the finer we can chop up each second, the better we know our location, the more data we can push through our networks, and the further our radar systems can see. So the good news is that modern atomic clocks already operate far below picosecond levels. So these clocks are now good to a second in 30 billion years. They're the best measurement devices on the planet, and we can use the same tools and techniques to demonstrate best-in-class inertial and electromagnetic field sensors. But you know, what's the catch? You can see these are laboratory devices. They're enormous, they're fragile, they're expensive, and they require a small army of graduate students to keep them running. So they don't run for 30 billion years, they run for a day, which is how long graduate students can stay awake. So to build practical devices, we need to move beyond just performance, and we need to focus on things like integration, operability in the real world, reliability, and cost. And that's, you know, that's what our company is trying to tackle. So Vector Atomic is building atomic technology for the real world. The company is a little over 6 years old. We have 52 employees, and we're located in Pleasanton, California, in San Francisco Bay Area. Unlike many of the quantum startups and a lot of startups in our area, we have no VC or private investment. So to date, we've developed our products on competitive government R&D contracts. Our focus is on building and fielding pre-production units and then turning those into commercial products, and we've started to do that. All the devices that you can see on this slide have all been taken out into the world, and they've all been operated on land, at sea, and soon space. So the clocks, the synchronization modules, the gravimeters are all operating at state-of-the-art for their form factors and in the relevant environment. If we kind of look at the guts of these systems, we design, build, and test many of the core components and subsystems in-house. This really allows us to kind of better control our supply chain, reduce size, reduce power and cost, all those things versus kind of integrating OEM subsystems. It also allows us to build fully embedded systems that can operate turnkey. I think for the purposes of this talk, if you look at that clock laser, it's a custom designed system by us, but it's built from off-the-shelf laser components, fiber laser components. Showing kind of the data, how these clocks can operate, and what going to this newer atomic physics technology can bring you. This is our evergreen clock versus the two current best commercial clocks. The Maser is that box-sized device, and the cesium beam, the microchip 5071A. Both those clocks play an essential role in GPS. The plot you see here shows accumulated timing error versus operating time. So the lower you are on the chart, the better. The less timing error you accumulate, the better. And what you can see here is that our EG30 slightly outperforms the best clock, the hydrogen maser, and it does it in less than a tenth the volume. And I think importantly, that maser can't really go anywhere. So to hit its performance specs, those typically live in a 1,000-liter environmental chamber where temperature and humidity are very precisely controlled. To prove our hardware can go somewhere, we loaded 3 of our first generation clocks, the generation before the one I just showed you, and a gravimeter onto a ship at this RIMPAC 2022 demo, where they were operated autonomously for 20 days. I think what we were excited to see is that the clock performance was nearly the same in the laboratory as it was out at sea. So we're able to kind of hit these highest performance levels for commercial clocks on a mobile platform. The details of all this are all the lab testing, the at-sea testing for these clocks are all covered in this recent Nature paper. So you can check out those details. We also separately operated this atomic gravimeter, which was able to measure part per million fluctuations in local gravity. We used that to compare to a gravity map, and that was used to reduce the error of the onboard navigation system. So you can see this Evergreen 30. This is now a commercial product that is offering kind of state-of-the-art clock performance in a small, rugged form factor. So 10x smaller than active masers, better phase noise, better short-term stability. How might you use this? Certainly as a frequency standard for things like low phase noise radar for this crowd, maybe a wavelength reference, for those doing quantum computing or for those doing optical metrology, kind of a box that you can lock all your lasers to, maybe with some wavelength extender. So, beyond just the standard 10 megahertz, 100 megahertz and PPS output, which, you would typically get out of atomic clocks, we also have a CW1064 output and a 1560 COM output. So to be clear, yeah, all that stuff is in that box. It's fully turnkey. You just plug it into the wall, hit the touch screen, hit go, and it will work for you. So in closing, I just wanted to thank our team. We built a lot of that hardware that you saw today under fairly challenging conditions that I'm sure a lot of you faced. COVID, obviously, chip shortages, labor shortages, very limited resources in the beginning. We have great facilities and equipment now, but it was certainly a humble beginning for us. So we're excited to be where we are. And definitely we want to thank our customers whose support goes far beyond just kind of writing the checks. With that, I'll conclude, and I'm happy to answer any questions.
Oh, those important customers paying the checks, how important they are. Please, Jamil, this is an Optica event, so you get obviously the Optica question. What can you do for the others, and what can others do for you? What are the key challenges that maybe we can help you with?
Sure. What makes these modern atomic devices great? It's the lasers. What makes them terrible? It's the lasers. That's what's the challenge for these systems is integrating these lasers in the system can really endow them with great performance. But for us, our competition is not, say university laboratories. It's, our competition is devices like these. And this microchip 5071A has a 7-year warrant or 7-year lifetime on it. And so in order for us to match that, we need lasers that operate for 7 years. We need lasers that don't, mode hop over time. We need things that can operate over temperature. So we have to kind of move beyond these really nice, very high performing lab grade lasers to something that's a little bit more telecom like in terms of its robustness. And that's a lot of what we've done, and kind of implicit in these sensors is we operate at 2 wavelengths. These clocks operate at 532, they're iodine clocks, and so we frequency double from 1064, very robust laser technology. And we also operate at 780, so we are able to double from 1560, again, kind of leveraging a lot of the work that's done in telecom. So we've gotten a lot of, go ahead.
Let me have a look at the screen here. These are the companies that register for the online industry meeting today. These are companies we have made a study, Puya Dianat and our team made a study understanding each company individually and knowing which where they fit in the supply chain. If you're looking for lasers today, we have in the room MKS, Hubner Photonics, OA Waves. We have, of course, Teraxion from the Photonics, Optica, Sager, Bandwidth 10, and coming all the way from beautiful Valencia, Fila, on super continuing generation. All of them are here and all of them are looking forward to talk to you. And I'm pretty sure that all of them will tell you that they don't mode hop and they work stable on temperatures. And for 7 years, well, that's nothing. They work forever. But in the meantime, allow me to bring to you 2 companies that my team scouted that they think they could be doing good partnership with you. One of them is expert in nonlinear crystals. The company is called Covation. Stuart Conver, thank you very much for your support to Optica. Tell us what you do, how you could help Jamil, and in one slide, how you could help the others as well. Stuart, you're on mute.
Thank you very much, Jose. Hopefully you can see my slide. And leading on from Jamil's talk actually is quite appropriate. So Covation are experts in nonlinear wavelength conversion based on periodically poled lithium niobate. The reason for that being a material of interest is it has a high conversion efficiency. It's a very flexible material that has good optical power handling, and you can tailor it to generate wavelengths right across its transmission window from anywhere from 400 nanometers right out to 5 microns. And as Jamil was focused on, our focus is on shifting this from a lab-based technology into a commercial, robust technology, so out of the lab and into industry. So to support that, we offer a range of solutions, right from chip-based solutions based on the crystal or a waveguide type solution, through to component packages with fiber coupling on the input and output, through to module systems, again with fiber coupling, and into more complex systems with added functionality. The sort of sensing applications that we support are anything that requires that very fine control of the latent source to drive the application. So good examples are atom and ion cooling, trapping, and interferometry, exactly as used in atomic clock systems, where you're looking at laser wavelengths to drive rubidium, calcium, strontium, cesium, iodine traps, as Vector are doing. And the end applications there being the timing and the gravimetric sensing applications. Switching it a little bit, obviously what you can also do with nonlinear optical crystals is generate photon pairs. So another really nice application is where you can generate an entangled photon pair of 2 different wavelengths and use that quantum entanglement or that coherence to image in the infrared and then detect at a silicon detector wavelength. So avoiding costly, expensive cooled mid-IR detectors, and indeed, when people talk about imaging with undetected photons, actually avoiding completely exposing your sample to the wavelength you're detecting. So again, our focus is very much on generating solutions, working with system integrators to put these nonlinear optical solutions into the quantum technology. And I'm more than happy to answer any questions that anyone has on that subject.
Thank you very much, Stuart, and thank you for your great support to Optica constantly, Stuart. Jamil, how does this feel?
Yeah, this does fit. I mean, I think you heard from us that we are starting from these kind of what we feel are more robust industrial lasers at 1064 and 1560, but we need to get to 780 and we need to get to 532. And so there is doubling in the system. And when you can see, or I mentioned we're stringing together right now for these larger systems, fiber-based components. Seeing that these devices are fiberized is great. That's kind of what we need. We want to splice them into the system versus having to, work in free space. Maybe for future smaller devices, we would do that, but certainly right now, what do we care about? We care about fiberized components with low insertion loss that do the job.
There's somebody else, Jamil, who wants to talk to you. The company is a very proud, extremely proud corporate member of Optica. The company is Hamamatsu. Michael Semlinger, what's on your mind?
Yes, thank you very much for the nice presentation. I was curious, you already mentioned microchip and the small compact atomic clocks that currently exist. So I'm curious if you actually want to go all the way there. Do you think it's feasible to really make an optical clock that can compete with that on a size wise as well?
Yeah, so I think you're mentioning the CSACs, the chip scale atomic clocks, which are probably the size of two matchbooks maybe on each other. That is an ambitious goal. In going to these optical clocks, you're adding a frequency cone, the 2005 Nobel Prize in Physics. Now you're putting that in one of your matchbooks, along with optical clocks. We are directly right now working on a 5-liter version of our clock, which is really kind of targeting the same performance as we get out of this EG30, and a stripped down version that's a liter scale, still good performance. Getting down to what you're talking about, 100 cc's, that really requires a lot of heavy lifting from integrated photonics. So I think there we have concepts, but I wouldn't put that that's not on our 5-year roadmap. That might be on our 15-year roadmap. So we have a lot of interest, but we're going to need to wait for probably a lot of people on this call today to do some of the work on, more kind of deeper photonic integration of the laser systems of the frequency cones. We're interested in working on that ourselves, but that CSAC has a single laser in it, 2 milliwatts, 50 megahertz bandwidth. So we tend to have much more challenging requirements, 1 kilohertz bandwidth, maybe larger powers, things like that. So I think we can get there, but it won't be the device in a couple of years from now. We'll step through from 5 to 1 liter, hopefully.
Thank you. Thank you, Michael. It is great to see you here. Jamil, there's somebody else who wants to talk to you, coming all the way from Keysight, Gabe Lenetsky. Hello, good afternoon for me, good morning for you.
Hi, Jose, good morning.
So I guess you can help Jamil with metrology solutions. Tell us how you could help him, and maybe I think you told me that you have one slide that could actually make a better understanding of the technology.
Sure, absolutely. Let me share my screen. So hi everyone, I'm Gabe Lenetsky. I'm from Keysight Technologies. I'm a business development engineer for our quantum aerospace defense and government solutions team. And I'm here to tell you a little bit more about what Keysight does and how we play an important role in the quantum industry, specifically quantum sensing research and development. And so how we do that is really based on our motto is that, we help design, emulate, and test to accelerate quantum innovation. So for example, in one of the areas that we see of interest, being talked about is single photon detectors or SNSPDs. Those types of technologies are taking off globally. And so we have a pretty broad portfolio of optical design and component testing solutions, from tunable laser sources as discussed here to optical power meters to optical attenuators. There's lots of different ways that we enable research in this area, also down to the PIC development, the PIC development for doing on-wafer development of, characterizing PICs. So there's a lot of ways that we help kind of innovate the single photon detection area that's related to quantum sensing, as well as quantum communications as well. More broadly speaking, and some of the ways that we are looking at how our other products or portfolio offering kind of helps the different quantum sensing areas, like for example, for Rydberg atom research, there's ways that our classical more state-of-the-art oscilloscopes, like our real-time oscilloscopes, and signal analyzers like our powerful network analyzers, offer a really useful tool to help characterize devices through classical network analysis techniques. So that's another way that we're seeing customers, clients using our hardware to help kind of do the early design and prototyping phase. And then of course, one of the other, already talked about technologies are DNVs, diamond nitrogen vacancies. We provide quantum control systems that are modular, really compact, AWGs, digitizers, down converters, for the goal of really for quantum computing, but a lot of what we're seeing is these systems are going to be used for doing early testing and prototyping of DNV chips. So one of the things that I'm interested in learning more about is how we can help enable this industry from going from the early design phase through the test and validation, developing more automated practices or steps to go from, test and validation all the way up to full scale production. And so I think myself and others on the team are very interested in learning how we can develop, I would say, workflows to get you from early design up to that, full scale production in order to provide, more, strong supply chain of quantum sensors to the market. So if you're interested in more of this information, you can reach out to me on LinkedIn, or you can also take a look at our website here. Any questions about that?
Thank you very much, Gabe. And of course, you want to get in touch with any of the participants today, or you have to send us an email and we'll make sure we make the introduction. Jamil, before we go to the next end user adopter of the technology, any final comments on Keysight metrology solutions or all the other challenges that you brought to the table?
Yeah, sure. I mean, what are the three parts of this? It's vacuum systems, it's lasers and optics, and it's electronics and software. And we're making a precision measurement. In the end, we need very low noise analog electronics that go along with it. So doing that characterization, any kind of noise you inject into your laser will show up and spoil your measurement. So certainly a lot of that measurement instrumentation we have. We might not have the latest version that Gabe was showing, maybe the eBay version of it, but it's great stuff, and we use it, and we can't do our work without it.
Jamil, I'm on record right now. If you want to try the equipment of Keysight, I pay myself for the shipping expenses. Let's continue with the meeting.
We can afford the shipping expenses.
Thank you very much, all of you so far, for the meeting. It's been great. A couple of you are texting me right now and they're saying, why is my logo not in this slide? This slide is only for the Optica corporate members who registered for this meeting. This slide will be published afterwards in LinkedIn and will be shared with all participants to understand which technology there is available for all of you from the Optica corporate members. So your logo is not there. It's simply because you haven't filled the application form yet. Let's go to the segment here with quantum optics technologies, and let's go to the company Inflection, who is going to talk to us today about their solutions for sensing, for timing, and for navigation. The floor and the attention of everyone goes to Inflection.
Hi, everyone. Thanks for the opportunity and inviting me out to spend the morning with you. It's a pleasure. Let me see if I can find the right button to share my screen and put it in display mode. Here, somebody tell me if I'm sharing the right thing.
It's crystal clear.
Oh, good.
All right. So, maybe just a very high level picture of Inflection. Our focus is on quantum systems using neutral atoms. And we go for neutral atoms as a platform technology to be able to tackle many applications. And we like this broad approach because all of the bits and pieces that we need to build a quantum computer are really the same bits and pieces that we need to build an inertial sensor and a clock and a microwave field sensor. And so as we mature in one area, we reap benefits in another. And so this allows us to feed our developments from one platform to another. We're coming at it from still a very commercial mindset, and so we're looking at making systems that are compact and rugged and portable, and looking to benefit from this community in the space of photonic advancements and technology elements that will allow us to miniaturize and unlock big advantages for the application space by scaling down the size and the cost. We have, you know, 3 product portfolios that I'll mention today in the sensing range. One of them being Ticker, which is, you know, not a sensor explicitly. It's a clock system, which is a thing that tries very hard to not sense anything, but uses atoms as a reference. And very similar to what we just heard from Jamil, it's a black box that will fit in a rack and give maser-like performance. We have Skywire, which is a quantum radio frequency sensor platform, which is meant to detect everything from very low frequencies to extremely high frequencies in a single sensor head. And we think that the Rydberg atom technologies have a very powerful place to play in the RF world. And then we've got Exact, which is our name for what's really a nascent product family that we're advancing towards having rugged systems for inertial sensing applications. You know, I wanted to give just a little bit of a picture of where I think we kind of are today and where we're going in the future, and just give kind of a global perspective. A few years ago, I gave a similar talk to this, and I put up this picture showing what laboratory quantum systems typically look like. And actually, I think we've come quite a long way, that these quantum systems now look more like this, where it's a more carefully thought out engineered system in a box that's still, you know, they're very beautiful boxes on the outside, and in the guts of them, there's still a lot of you know, touch time and delicate handwork, lovingly handcrafted by artisan scientists, I like to say. And where I think we're going to get to in the long term is a quantum integrated circuit, devices that allow us to take all of this power and capability and squeeze it into a little box. And I would argue that this is the same picture of saying, here's a you know, we're at the age of VHS and Betamax, and we're arguing about ions versus atoms versus superconductors and NV diamond centers. But where we're really trying to get to is smartphones. And so there's a big, long jump ahead of us. So, you know, take everything I say, and I think everything in this group with a little bit of a grain of salt, because we're probably wrong. We're gonna learn a lot. We're gonna make a lot of mistakes. We're gonna go down some product roadmaps that end up being dead ends, and that's great. That's just part of technology development. But it's good to keep in mind that the end goal is still a quantum future with little handheld devices that allow you to play whatever the future equivalent of quantum cat videos ends up being. In the sensing space, there is kind of a harsh reality that there's a big markets to serve, but they're already being served. There's already very mature technologies that we're competing with. So there's a little bit of a quantum chicken and egg of, do I go with this classical chicken that I know is going to be delicious, or do I open up what's inside of this egg and deal with that? That might be much better, but is going to take a while to mature. And so we have to compete on more than performance. We're building, you know, sensors that have to be very high performance and very reliable, and they've got to go somewhere to be useful. So, you know, we're a little time limited, so we can't get into all of the fun details. But so I wanted to just talk a little bit about some of our recent activities to get things out into the world. So this is one version of that, where our quantum RF team wanted to get some sensing demonstrations done out of the lab, and so they took what was literally a couple of tables full of optics, and they squeezed them onto a couple of racks, not taking too much time to really ferret all of the space out of the box, but just get something that we could move around. And we found what I assume was the smallest van that the team could possibly rent to squeeze all this stuff into, and drove it out to New Jersey and made some sensing measurements out there. So we are starting to get some of these devices that even though we've just barely gotten them to work in the lab, we can advance them out into the field very quickly, because those technology elements are starting to become more mature. So our clock team didn't want to get shown up, and so they said, great, we're going to do the same thing, but we're going to do it in the desert, and we're going to run our clock while driving down a highway in the desert and at night. And I don't think that at night makes a difference, but it sounds like it would be harder. Our team in the UK, these handsome gentlemen, said, well, we can do better than that. So they went and made friends with somebody with an airplane, and they went and took our clock and racked it up in the airplane and tested it in flight, and were able to show good operational performance, as well as we were able to measure with the reference oscillators that we had on hand, that the clock was behaving itself through flight operations. And because they just wanted to show off, they also happened to bring an ultra-cold atom system with them, and demonstrated a Bose-Einstein condensation in flight, and then did Bragg interferometry on that BEC during the flight trial. And so all this is a partnership with Kinetic and BAE Systems, and we were able to demonstrate that these things operated during takeoff, flight, and landing. So there's lots of more wonderful things I'd love to tell you about, but our time today is limited. So maybe I'll wrap up saying that sensing and timekeeping are finding their way out of the lab, and there's a commercial clocks that, like the wonderful system that Jamil just told us about, and our ticker platform are both rapidly getting out in the field, and the other sensing modalities are following along, and they've got a long way to go, but we're definitely on our way there. So I'll jump ahead on the Optica question, since I had a minute to add a slide while we were chatting this morning. What can Inflection do for you? Well, we have a lot of other activities beyond our sensing device portfolio. We have a whole division focused on component technologies, building UHV components and systems, building atomic sources, building complete instruments. We have a lot of activity on workforce development. So what I'm showing here is a picture of a new product from us. This is the Desktop Mop, which is a system targeted to teach quantum physics through the lens of cold atoms. So that this is meant to be something enabling for research and teaching environments. And we also have Octant, which is an online service that allows you to through an online web portal access a piece of equipment in our labs and produce those Einstein condensates and manipulate and try to understand quantum devices. And then how can you help us? Well, we really love the open communication collaboration, like these types of Optica meetings. I think this is really valuable for the whole community, that we keep talking to each other and telling each other about what's happening in our labs and what our challenges and needs are. So first, thanks to Optica, please keep holding these sessions. We got to build a scalable and sustainable supply chain. I mentioned that everything we have is currently lovingly handcrafted by artisan physicists, and that makes things hard to get out into the world. We've got systems that are expensive because there's a lot of touch time involved. So I have the same laundry list that Jamil mentioned of vacuum technologies, laser technology, electronics, software. These are all areas where we're continually faced with make-buy decisions, and we're very open to partnership to develop those application spaces and those component technologies. So maybe I'll stop there and see if there's anybody who has questions for us Inflection, and thank you for your attention.
Thank you so much, Evan, and thanks for the nice presentation and impressive work that you've done in here, and it's been these sensors have been flight tested and all that. Now I have a quick question, and from the technical point of view, what are the top 2 things that are keeping you awake at night? And there are lots of folks from optics and photonics in here. I'm sure they are going to help you sleep better at night if you know the top 2 things. So
I mean, as Jamil said, lasers are the biggest thorn in my paw. The single source of downtime, the largest source for downtime on our teams is laser systems, and ferreting out the challenges of those operations. Reliability is a key issue. sustaining good performance over a large operating range. Most of our supply chain is still people who are born out of our DNA, which is research and development activities rather than real hardcore ruggedized product development. And those two areas kind of, they pray at different temples. The R&D is rewarded by innovation and creativity, and product and manufacturing is rewarded by consistency and reliability, and they're different gods, so to speak. So we need to have some more of this community praying at the temple of quality assurance and reliability, so that we can start getting to more predictable technology offerings. But at the same time, we do need all of that innovation. We need, for us to really scale up, we have to engineer the physicists out of the box, and that's going to take things like PIC technologies to be able to make that laser system go from a $150,000 bomb to a $3,000 bomb to actually be able to serve real markets.
Okay, and let me bring in someone that may have an interesting technology with you. I would like to bring in Brendan Isaac from Freedom Photonics. Brendan, I know you have some interesting technology that you want to show, and you have one slide. Why don't you share it and let us know what you do?
Yeah, sure. Unfortunately, my cat heard you call my name and now wants to sit right in front of the camera. Yeah, you guys can see my slide here?
Yes.
Cool. Okay. So yeah, you can think of Freedom Photonics as sort of a component and laser supplier for systems like this. So we have a rich history in 3.5 semiconductor devices, particularly lasers, whether it's high power Fabry-Perot lasers, widely tunable single frequency lasers, or DFB lasers, which is sort of our currently our bread and butter in this quantum sensing, atomic sensing area. And you can see sort of a staple here in the center panel here, highlighting our gallium arsenide 780, 795 nanometer DFB laser. So this is a single frequency laser. You can see the spectra of a couple different lasers here on the bottom, showing good spectral purity, high side mode suppression ratio. An individual laser can tune about a nanometer or two. This is a couple different ones, but so this covers sort of a lot of the interesting wavelengths that are currently people are looking at in rubidium 778, 776, 780, 795. But on top of this, on top of the DFB laser itself, we're often also integrating SOAs. And so this enables a little bit of a power boost, but also functionality. So properly designed, an SOA can give you very high extinction. So in this case, where it's properly designed, we can get over 70 dB of extinction using an integrated SOA. And I would say that's most commonly what we're asked for, what we sort of developed mostly. We're also interested in more complex gallium arsenide PICs. And this is an example shown right here, where we have modulators, photodetectors, splitters, mixers, so that we can incorporate, generate sidebands for various applications, do on-chip heterodyne detection. And so sort of the highlight is Freedom Photonics in the quantum sensing space is our 780, 795 nanometer DFB laser with an integrated SOA. But we're also developing these more complex PICs that we've heard about from Vector Atomics and Inflection, sort of looking towards the future. The nice thing about DFB lasers is that they do have very stable wavelengths. So this is a single example of a single laser run over 2,000 hours. And basically all these little jumps are just a resolution limit of our optical spectrum analyzer. In addition to just lasers themselves, because of our sort of expertise in packaging, we also get involved in custom sensor head development for technologies such as NMR gyroscopes, magnetometers, atomic clocks, Rydberg sensors. And these are some of the examples over here. With this one in particular, this is about the size of a golf ball. So this is using some of our experience working with micro optics and laser packaging expertise. And finally, most of this is focused on rubidium 780. That's sort of the most common atomic species that is being researched right now, but there's a ton of other ones. And this is where I think photonic wire bonding, which is an in-house capability we have, is really interesting because it enables us to take, our plethora of, more mature laser technologies in gallium arsenide and indium phosphide, and connect them to, various nonlinear PIC platforms such as lithium niobate or silicon nitride to generate these sort of exotic wavelengths that aren't available through conventional 3.5 semiconductor approaches.
Thank you so much. And please post the questions for Brendan in the chat. There are a couple of questions actually that I think one of them is for Evan. Arthur Lobo from US Navy, why don't you ask your questions live from Evan? All right, I'm not sure if he is.
Oh, he says already answered.
So okay. So I guess the question is I read that for Evan so that he can answer to everyone. The question was was this Skywire developed from the DARPA Quantum Aperture program?
And yeah, that was one of the programs that supported our initial development in quantum RF systems, and so it's a big part of the strategy of these new technology developments for us at least has been some combination of non-dilutive investment in development programs that hopefully help us get springboarded and allow us to then minimize how much expensive dilutive investment we have to put into advancing these things towards product. But yeah, we're very grateful to the support from DARPA and the U.S. military on some of our development activities here.
Okay, and there is actually a question for Gabe, from Keysight, who did the presentation. So Gabe, the question was, how small can you make the Rydberg atom RF sensors with the atomic vapor cells?
Yeah, that's a good question, and I put a link to in my answer in the chat, but there are a couple different companies too. There's a company called Rydberg Technologies that also is providing Rydberg sensors on the market as well. Basically, they're still large. I don't think there are any very compact ones that are on chip yet. So depending on how small these things are able to how small you're able to make them, it's going to be an interesting form factor for how, I don't know, either aerospace defense contractors develop them, or the Army or whoever might be using them. It's interesting how they'll be able to try and scale them down to a more compact form factor.
Okay, and everyone, Rydberg actually is an Optica corporate member. So if you want to get connected to Rydberg, just reach out to me or Jose, and we'll be happily connect you to them. Now, with that, I would like to move on to our next presentation, next company that I'm super excited about. They have fantastic technology, and I'd like to hear from them. It's going to be the presenter is going to be Kayla Johnson from SB Quantum, all the way from Canada. So Kayla, the floor is all yours.
Yes, hi, thank you. Just let me share. All right, is it sharing all right?
Yes.
Okay, so hi, I'm Kayla. I am a physicist working at SB Quantum. And at SB Quantum, what we do is we develop quantum magnetometers, which are based on NV diamonds. So, slide. So there's obviously the Earth's magnetic field is everywhere around us, and it's an incredibly underutilized resource. So even though it's everywhere, we tend to not use it, except for in things like navigation. So if you are to open like your Maps app and you see your little dot that points in which direction you're facing, that's because of magnetometers that are found in your cell phone, except it tends to point the wrong way because the data they have to reference that is incredibly noisy. So our vision at SB is to provide data as a service. So we want to provide high resolution, game-changing data based on quantum sensing. We use quantum sensing and denoising algorithms to be able to provide that data. And we have a lot of markets in which we can use this for. So I'm only going to talk about two of them right now because of time constraints, but basically we do it in mining and exploration, navigation, and also in defense application. So in terms of mining and exploration, what our technology can offer is a full tensor magnetometry. So typically magnetometry is not done in tensor. So if you start applying that, you have about 9 times more magnetic field maps per point, which can be incredibly useful for drilling and also in navigation. So we work with Spire in an NGA program called MagQuest, which is done with NASA, basically on rebuilding the world magnetic model, but I'll get a bit more into that after. So the world magnetic model is this map you can see here on the lower left. Basically, it could be used for navigation, and it is, but the world magnetic field changes every 5 years, which means you have to retake a new mapping all the time. Along with Spire, which is a UK company, we're putting our magnetometer on a satellite, and we're using our own machine learning compensation algorithms to take away the noise that comes from this satellite so that we can have an incredibly precise magnetic mapping of the world. Now, this is 10 times cheaper than the solutions we do that are there now, mapping the world magnetic model, and the size is incredibly smaller. So we go from about a bus-sized satellites array to just something that's about a guitar size with the deployable boom. And that's incredibly useful because, like I said, every 5 years, we have to redo this model. So cheaper once is incredibly cheaper over time. We also do a lot of exploration. So we've completed, it says 7 here. I think some of our team just came back this morning. So 8 pilots in terms of mining. There's about 400 million in this market that could be tapped for surveying. So it's an incredibly interesting market that we work with. What's really nice is that our sensor is quite small, so we can put them on drones eventually for airborne, non-invasive surveying. Also, it can be done by foot because the magnetometers are quite light compared to a squid, which is incredibly difficult to transport and hard to navigate around. So that's one of the applications. Also, limitations from other devices is that they're only scalar they only do scalar magnetometry, sorry. And like I said before, we offer full tensor magnetometry. So how tensor works is basically, if you only had scalar, you could scale the magnetic field right at the first layer of the Earth and know exactly what your magnetic field is. With a tensor, it's kind of a comparison from an X-ray to an MRI. So you can visually map every layer what the magnetic field is, which is incredibly useful to find distance for spots to drill. So here's an example of our maps. Now, the first map on the lower left was done by a pilot in Nunavik. And then on the second one, we have a map done by foot by some of our team for surveying. And just for this survey, it was about 10 times better on speed and cost. And below, on the lower right, we can see the refined geology map made by our geophysicists. And this started showing aspects in the map that just weren't seen before with other pilots, but that we could pick up using our tensor magnetometry. Now, how does our magnetometer work? This is a bit more of the nitty-gritty, but basically we use NV sensors, which have their own crystalline structure, and we input a laser, microwaves, and we're able to optically detect magnetic fields from that. So that's very useful because the diamond itself is invariant to temperature and has a predefined geometry, which allows us to extract a full vector, and it's the reason why we can do tensor as well as vector magnetometry. So I have a little video of our device at work. Basically, this is passing a magnet in front of it, and as you can see in the corner, we can detect it immediately with our sensor, and it can detect things even as small as a credit card, where here we can see our other bump. So like I mentioned before, they're very stable at room temperature. They do vector magnetometry. They don't have heading errors, and they're incredibly compact. So I have one right here, my hand. They're super light and compact, very fun, and can be put onto drones or any sensing platform if we want. The diamonds are, they don't have any drift with temperature or geometric drift because of their crystalline structure, and they have a high dynamic range and tolerance to gradients. So for now, our magnetometer consumes about 4 watts, which is incredibly low, but it was a necessity for the NASA program that'd be under a certain wattage, so very low power consumption. It weighs about 0.5 kilograms, and we have a sensitivity of about 500 picotesla per square root hertz at 1 hertz. Our magnetometers have gone through winter surveying and as well as radiation testing and vibration testing, which again, I have a video, it might be a little loud. This is the vibration testing. So they've been tested for space and launching, and they've also been tested by our CEO under driving conditions, where you can see he's very unsafely driving the magnetometer around in his car. And if you look in the loops, you can see him turning, and we can see the turns in each orientation. We've also recently sold a device in France, and we're looking for beta users. This is our team, quite a small startup, and we've also recently had Lillian Childress join us, who is an amazing scientist in NV magnetometry, so we're very happy to have her. And that's about it for me.
Thank you very much, Kyla. Amazing tech. I would like to highlight that Optica does not support beta tests while driving, and also that if you can survive a Canadian winter, you can survive anything. But we have some questions in the room. The first one is coming from a metrology company, LaTeX. Marcello, what's on your mind? Marcello Vinetti?
Hi.
Yes.
Hi, can you hear me?
Loud and clear.
Yeah, okay. No, I was just wondering whether you can use this technology also to do archaeological survey. What is the say the size that you can resolve with it?
Archaeological survey, sorry?
Yes. Since you were saying that you can measure magnetic anomalies and kind of map the 3D the Earth, and then one of the possibility would be to find out whether there are archaeological sites underground based on the presence or absence or the presence of voids, for example, that should have some kind of effect on the local magnetic field.
Yeah, so of course we have about a 0.500 pico sensitivity per root hertz. So magnetic field, the way it works is it depends how far away you are. So we haven't done any archaeological survey, but definitely if the things you're trying to detect have a large enough magnetic signature, you can definitely do that. A lot of people do pipe detection underground, which have quite a strong magnetic field, and that's something we could do potentially. And we're open to new projects and new collaborations. So if you write to me about the needs, we could definitely work something out. and try to find
Yeah,
out.
this was just out of curiosity for my personal.
Grazie
Yes.
mille, Marcello, and thank you very much for everything that LaTeX is doing.
Thank you.
Kyla, we have very little time and a lot of questions for you. So let's do this challenge. The first one, how does the supply chain of diamonds look like?
The supply chain, there's a lot of startups that are currently doing diamonds. We actually offer characterization processes. So a lot of startups, we collaborate with them to evaluate their diamonds, but it's definitely an up and coming thing. Different companies have different needs. So I would say there's quite a few startups. There's Element 6 that's very big on making the diamonds. And yeah, that's...
You know, when you tell me that the supply chain is based on startups, I get worried about that. Matthew Markham from Element 6. Would you like to comment? 1, 2, 3, waiting for Matthew to unlock.
Yes, sorry. Yes, I'm trying to find the button. Yes. So definitely, if you do want diamonds, we come and reach out. I put my my LinkedIn details. So just reach out to me, and yeah, potentially we'll be able to find you the right diamond. We supply a range of different commercially available diamonds. So for sensing applications, we have our B1 and B14 materials, but we also do a number of other sort of materials in our research team. So please reach out if you've got questions or want to know what is the right sort of diamond for your application.
Yeah, great to have you in the room, Matt. Allow me to go now to Arthur Lobo from US Navy. Arthur, what's on your mind? I'm going to read the question. Yeah, Arthur, loud and clear, yes.
Okay, so the question was the radiation testing. What kind of testing was that? Did it include charge accumulation kind of radiation testing where the qubit is eventually going to collapse, or is it transient to test for transients like muons and heavy ions and neutrons and so on and so forth?
I don't have all the details of the testing, but it was definitely more for heavy ions. It was under the MacWest project, so it was to test if we could go to space. And so if you want more details, you can write to me. I could get the exact tests that we do and send them right back to you.
Arthur, we are loving your questions, and I'm already getting some requests of people wanting to get in touch with you. So there will be a few introductions following up. Kyla, there's some people I want you to meet. The first one is from a company called OE Waves. OE Waves is developing the narrowest ultra narrow line width lasers, but have many more things that they would like to showcase at the meeting. The floor and the attention of everyone goes to OE Waves. Ori Johnson.
Hey, thank you so much. Thank you so much. Yes, OE Waves, we are the manufacturer of ridiculously low noise photonics, starting with our whispering gallery mode resonator based lasers. So what we do is we work with a variety of vendors that provide the laser diodes in the wavelengths that are needed, and connect them with our billion level Q whispering gallery mode resonators to get line widths down to sub-hertz. So the narrowest lasers that I've seen shipped in my year with OE Waves were about 300 millihertz instantaneous line width. Now, that's ridiculously narrow for a lot of applications, and but having that narrow line width and the other stability, for example, low RAM that comes with this laser design, provides or allows people to simplify other system design. And now for those people here in the room that are building their own laser systems or have other lasers that they're using, we provide laser noise analyzers as well. These provide phase noise and intensity noise at extremely good levels. So this is what we use to measure our lasers. And then the third thing I want to highlight is our compact photonic systems technology that is available to use in partnership with all the people here. And so the little device there that is a penny-sized device has a couple of lasers in it, detectors, and a total of 29 different optical components combined in there for a RF generation.
Thank you very much, Ori. Thank you for being here. We started with them. Let's finish with them. Allow me to give the floor to our sponsor today to tell us how they can help everyone in the room. Ahmad, tell us how from Optica's side, in the field of quantum sensing, you can help this community.
Sure. Thanks very much, Jose. And it's great to be the last I've listened to all of this presentation and see what is the devices being designed and used in this quantum sensing and how is OptiWave can help. Basically, OptiWave have different software packages which can be used to design the devices, which mentioned from lasers, from detectors, from photonic integrated circuits, and so on. So relevant to this meeting here, we have OptiSystem, OptiSpice, and OptiFDDT and OptiMode software, which can be used for designing, as I mentioned, the devices and also characterize these devices in a system. So in a system software, we have over 600 components and visualizers can be used to simulate and analyze the system. We have the SPICE software, OptiSpice, which can be used for designing optoelectronics component, and it's also integrated with EDA vendors, which can be used for PIC simulations and layout characterization. In terms of FDDT and OptiMode software, it can be used for creating compact models for the devices. And finally, I just want to say that all of these packages work cohesively with each other and enables the user to design the devices and characterize them and find issues and debug circuits which you might be avoiding after you make your devices. So you can pre-analyze your kind of system and devices. Thank you. If you wanted to download our software, basically you can go to our website and download 30 days free trial of any of these packages or all of these packages.
Thank you, Ahmad. If you want to get access to this 30-day trial, please let Ahmad know, and also let us know. We will share with everyone the link. Thank you very much, all of you, for a great meeting. I would like to let you know that at Optica, we are really trying our best to connect the industry. So it means that after this meeting, you check the participant list, pay some attention to the participant list, and identify which companies you want to get in touch with. There is where the job of Optica excels. We will make one-to-one introductions. That's why we are here. We are not event organizers. We do our best. And I think this event was cool, but it's about the connections. You also find online everywhere in LinkedIn the participant list in a visual form with our Optica corporate members showcased in a supply chain. For us, it's super important that we build a puzzle and all of you are at peace. Until the next time, see you soon. Bye-bye.
Bye-bye.
All right, so allow me to ask now my IT colleagues to disconnect the live stream. And I would like to, now that we are in a private meeting room, nobody's watching, I would like to let you know, all of you, thank you so much for the support today.